Hello, good morning, and welcome to this course. This is the Information Theory and Coding for fifth semester, 18 EC 54. So, in this course, today we will see the basic introduction to this course and also the course logistic. So, initially we have the course details here. This course is of 3 credits, and you see here the semester end exam has a 60% weightage and continuous evaluation has a 40% weightage. And we have totally 40 lecture hours in this semester. The prerequisites for this course are mainly the probability theory and little knowledge about linear algebra. And regarding our class hours, we have some of the lectures as recorded sessions and some of them are live sessions. On Tuesday, we have the classes from 10:15 to 11:15 in the morning. And on Thursday, we have between 9 to 10. And on Saturdays, we have 11:30 to 12:30. Regarding the course outcomes, so we have listed here about 6 points. That is, what do you get at the end of this course? So when you completely study this course, you will be able to understand all these points. Some of them are at the understanding level, and others are like applying the concepts and also analyzing the concepts. For example, the first one is to understand the fundamentals of information theory. So this is regarding the understanding of the basics of information theory. For example, what is information theory and how to represent the information, and what is the application of it, and so on. And then in the next outcomes, that is 4.2, you will be learning how to apply some of the source coding methods that we learn in this course. Similarly, then in the next outcomes, you will be able to understand, also apply different channel coding methods, and you'll be able to appreciate those methods, because when the information is transmitted from the source to the destination through a noisy channel or maybe noiseless channel, how these different channel coding methods will help us to recover the information. All these things you'll be able to appreciate. So this slide basically gives the outcomes of this course. So at the end of the course, you will be having these abilities. So regarding the course web page, I have already created the Google Classroom and invited all of you to join the web page. So you may do so. And here is the link, as well as here we have the QR code. You can scan this QR code and directly enter the web page where all the course materials will be shared. And then we have the course feedback form. So this is the link for the course feedback. So if you have any suggestions or if you have any issues regarding this course, you may please write to me. I will take suitable action and I will try to incorporate whatever suggestions you have mentioned in the feedback form. Next, regarding the evaluation. So as you all know, we have 3 internal exams. Apart from that, this course will have 1 to 2 quizzes per module. So these quizzes, maybe some of them are of multiple choice, where you need to pick out one right answer out of multiple choices, or some of the quizzes may be descriptive, where you need to describe or explain some of the concepts. And these quizzes, some of them could be online, and when you join the college, maybe in October or later, you will also have paper-based tests. Even sometimes the online tests could be paper-based, where you need to write the answer on the paper, and then you need to scan and upload. And then regarding the assignments, you have at least 1 assignment per module. And again, we have a mixture here. One is some of the assignments sometimes may be online, and some of them may be paper-based, where we need to write the answer on the paper or a book. And regarding the assignments, some assignments will be coding assignments and others will be descriptive. So when I say coding assignment, mainly you may need to use the C programming, or maybe you can use, if you are aware about MATLAB, you can use MATLAB to execute some of the codes. So this will give you a better understanding of the concepts. That's why we have some of the assignments as coding assignments. Please note that plagiarism will be treated seriously. That means I don't want you to copy others' answers or others' code directly. You need to understand the assigned question and try to solve the question by yourself. And also, I have one concept called as bonus, where if you answer some selected questions, which are called as bonus questions, you get special points or marks. For these questions may be oral questions, a descriptive answer, or sometimes this may be problem solving. So these bonus questions will have certain weightage, maybe 1 point per question, or half marks per question, and so on, or maybe sometimes 2 marks per one question. And these the marks you get by answering the bonus questions will be directly added to your continuous evaluation. Regarding myself, I'm Jagdish Bhatt, and I graduated from NTHU. And you can meet me when you come to college at 1402 of the teaching block 1. And this is my email ID, where I'll be using this email ID to send you most of the course materials and also some notices regarding this course. And most of our classes, when we are online, will run through the Google Meet. And if you have any questions, maybe I'm not talking about the live courses, beyond the live courses, at any time, if you have any questions regarding this course and you need more explanations exclusively, we can discuss using the Google Meet. But please write to me beforehand so that I can get ready. And when you come back to college, we will have the contact hours. That means if you have any questions regarding a specific topic or some issues with the course, you can discuss on Mondays between 4 to 5 p.m. And of course, you need to write me an email so that I will make myself available for the discussion. And my research areas are in device-device communication, edge computing, and caching in 5G networks, and some algorithms for ICT and smart city. So this is regarding myself. And now we'll go to the course contents. So in the upcoming slides, we will see some details regarding the course. So these are the fundamental details regarding the course. So we study here, for example, in the first module, we will study the background about information theory. Maybe at this moment, I guess you have no background regarding the information theory, but you have some background regarding the requirement of information theory, that is the probability. You know how to compute the probability of different events and so on. So we will build this course based on your knowledge of probability theory. So here, initially, we will talk about, especially in this course, in today's lecture, we will talk about the introduction to information theory, such as what is information, what is the need of information, and what is the need of information theory in particular, and so on. And then in the upcoming lectures, we will try to understand how to measure the information, whether the information can be measurable. If so, then how can we measure it? And there is also another term called as entropy or the average information content. We will see what's the mathematics behind all those terms. And also then we will see specific type of messages. Maybe a message could be a short message or a long message. When we consider a long message, the different parts of the message may be dependent on the previous messages, or maybe they are independent. In all these cases, how to measure those informations, or do they have any particular characteristics that we are going to study here. So the first module will revolve around information and how to measure the information, how to represent the information, and so on, because everything what we represent here is in the digital format. For example, if you consider a mobile phone, where we speak, our voice is converted into digital, and then it is transmitted over the channel. And finally, the called party or the destination will pick up our call, and we have the conversation going on. And in that case, the information has to be represented in the digital format. And also, this information should be, when we transmit that, it should be measurable, because we want to represent this information in certain, with certain unit, that we will see those things in this first module. Or that is the motivation to study the first module. So then in the second module, we will see the second component of this course, that is called as a source coding. So when I say the word coding, that is like representing any information in a coded format, coded or a crypted format. So how can we do that? At the source side, how the information can be coded so that we can achieve some benefits out of it. So there are different algorithms suggested by the experts. So one is called as a Shannon's encoding algorithm, and also Shannon-Fano encoding algorithm, the next version of that, and KM uh, and Huffman coding. All these are different algorithms used for performing source coding. Those topics we will be studying in the second module, that is source coding. In the third module, we will be studying the information channel, because the information what we have has to be sent through a channel. Maybe in case of a mobile communication system, this is through a wireless channel. But if you consider the communication between two computers through a LAN, maybe that is through a Ethernet cable, wired cable, and so on. So whether this channel exhibits any kind of property, of course, yes. That can be again modeled as a mathematical system. So that we will be studying in the third module. And in the fourth module, we see something called error control coding. So in case of error control coding, again, we have the word here, coding. So this coding or encrypting is done at the channel level. So in the second module, if you go back here, I use the word coding here, source coding. And here I use error control coding, or in general, all these are called as channel codings. So these here, when I say the word coding, this coding is done on the information when it is transmitted through the channel, because channel may introduce some kind of noise. It may be wired channel or wireless channel. So in that case, how can we represent the information in a secured way so that it can reach the destination safely, or at the destination it can be readable or understandable? So that is done at this process, that is called as channel coding or error control coding. So we have different ways of doing that. One is called as linear block codes, where the information is considered as a block, that is a set of messages, or binary cyclic codes. That's another way of representing the message when it is transmitted through the channel, and so on. And in the fifth module, that's the last module, we have convolution codes. So this is another type of a channel coding method, very popular. And we will see how to encode the data or code the data, as well as we see how to decode the data. In order to decode the data, we use a specific algorithm called as Viterbi algorithm. So these all these algorithms are used in the present communication system. So as I mentioned about these 5 modules, this is the 5th module, and we have the 4th module. Here is the 3rd module regarding the channel, and we have the 2nd module here regarding source coding, and the 1st module is a general introduction about the information theory. So please don't get confused by these terminologies, because in today's lecture, we will be seeing all these terms in detail, and also I will give you illustrative examples to understand this. Since I talked about the course content at the very beginning, so we have all these terms at the very beginning. Otherwise, we will be seeing these terminologies one by one in the upcoming lectures. So regarding the course material, that is mainly books, which books you need to refer. The key book will be this: Digital and Analog Communication Systems by Kumarasamy Sam Shanmugam. And the second book is Digital Communications by Simon Hykin. And again, these both the books are from Wiley Publishers. And also we have another book that is Information Theory and Coding by Dr. Haribhat and Ganesh Rao, that is of Cengage Publishers. So from this book, we have very limited contents, very few pages of information or the coverage. But these two books will cover most of this course. Especially this is the first textbook, or in the course contents you might have seen text one, text two. So here text one is the first one here. The digital communications is the second book or text two, and this is a reference book, that is reference 4 in the um, course content. But from this book we have some of the concepts. So at the during the online courses I will make some of these contents available to you, and later on when you join back you can have your own copies, maybe from the library. Okay, now let us move on to the formal introduction to this course, and it's a very brief introduction. Let us talk about information now. So the first question is, since we have the title Information Theory and Coding, the first question is, what is information? So here we have the answer. Information is nothing but any message. So we have different examples here. Another way of representing information or talking about information, or the definition of information is, or one of the characteristics of information is, it carries some knowledge, and recipient is able to interpret that. So information is nothing but it is something or anything that carries a message, and this message is basically a knowledge, anything that is new, and the receiver, whoever is the intended party, he is able to understand it or interpret it. So the different sources of information are, I have mentioned some of the sources here. First one is the human brain, because brain thinks about many topics or issues where information is created, and then we human beings express our thoughts maybe by speech, right? So when we speak, currently I'm speaking, my voice carries some information, or it carries some knowledge or some message. So the people who knows my language, currently English, can understand this or interpret this. So this is the information. So when we see this image here, this is a newspaper, right? So this carries some information here. So if you know the language here, you can read it through your eyes and then understand what is this, what they are saying. Similarly, we have some digital sources of information. For example, a TV. TV gives us some audio signals as well as video signals where we can watch, and we get some knowledge. So TV is another source of information. Similarly, books. It may be an ebook where you read and get some information. Similarly, we have a picture here. The picture conveys some information. For example, this picture is of a globe, a world map, or so on. So this carries some information. By seeing this, you can say what it is if you know this, right? So all these are informations because they carry some message. When you speak, some message is being conveyed or some knowledge is being transmitted, right? But we will not be discussing about this kind of information. I mean, at this level, we will be seeing the mathematical properties of this information, because our main objective is listed here. Maybe in the next slide, we have listed why do we need to study this information theory. Okay, because the main reason is we use them daily. How do we use them? There are different categorizations here. For example, the first category of information is called as syntactic information. So that is related to the structure of the message. So when I speak a sentence, there are different words that forms the sentence, and these words are chosen carefully sometimes when I speak. So all these words in a sentence will have a certain structure. So that is called as a syntactic information. This is a daily activity. When we speak or when we write, this happens. Next one, semantic information. That is related to the meaning of the message. So here, what's the key point is the meaning. So if I have a sentence, when I speak a sentence, there may be many words or many letters, but ultimately what is important is the meaning. Okay, that kind of categorization is called as semantic information. Thirdly is the pragmatic information. So here, this is mainly based on the usage and effect of the message. We have examples to these points, these categorizations. We have examples coming next, where you will be able to understand this more clearly. But regarding the pragmatic information, so here the usage of the words and what is the effect of this information or these words on the listener or the receiver, that is more important. So these are the three classifications of the messages that when we speak daily, that can be categorized into these three sections. The information emitted from different sources can be categorized either as a syntactic or semantic or pragmatic. So the key points I have listed here. For example, in case of syntactic, the structure or syntax is more important. In case of semantic, the meaning is more important, and otherwise, in the case of pragmatic, the usage and its effect is more important. Let us see some examples. I think here you'll get a better idea regarding these three classifications. For example, the first sentence says, I eat fish by fork. The second sentence says, I use fork to eat fish. The third sentence, Karnataka reported 200 COVID-19 cases. The fourth sentence says, in Karnataka, especially Mangalore, reported 200 COVID-19 cases on August 28. Now we need to understand from these four sentences to which categories we can map them to. Let us see. The first and second. The first is I eat fish by fork. Second is I use fork to eat fish. So the first and second are syntactically different. The first one, syntactic. The structure of the messages are different here. Here it says I eat fish by fork. Then I say I use fork to eat fish. The structure of the sentences are different, but semantically and pragmatically they are equal. Semantic. There's a meaning is the same. I eat fish by fork. That's it. And also the pragmatic, the usage of the two sentences, and the effect is I'm eating fish. That's the effect, right? So these two are the same in these examples, that is 1 and 2. Now let us examine 3 and 4. What happens in 3 and 4? In case of 3 and 4, they are syntactically, semantically, and pragmatically different. Why? Because Karnataka reported this many cases, and Mangalore reported so many cases on this particular day. The structure of the messages are totally different. The meaning conveyed is also different because this says Karnataka is a large state, but it says in Mangalore it reported 200 because Karnataka may report these days thousands of cases. Here it says 200 cases. So these two are not same. The meaning is not same because Karnataka can report 5,000 per day right now. So the meaning is different, and also the effect is different because here the effect it says on a particular place we have 200 on a particular day Here it just says roughly 200 cases on which day, we don't know. So the effect is also different. This is more detailed, so gives you more clear information. So these are the ways in which we can classify the information under these three filters. These are the things we do every day. Now, what is information theory? This is the title of the course, Information Theory. So what is information theory? It's a science that deals with what? The concept of information. We saw what is information. Information is nothing but a message that gives you some knowledge and you can understand that. So information theory deals with what? It deals with information, of course, and its measurement and application. So in this course, we will be seeing these two parts, that is measurement and application. So this is what the engineers do. Information, of course, we have in our surrounding, maybe a birds or animals, which generate some voice when they communicate with each other, or the sound of breeze, etc., are information. Some sound, they have some pattern, but we try to measure it and we try to apply that somewhere. So now, the elementary unit of information is the binary unit, maybe 0 or 1, or true or false, yes or no, black and white, etc. And what is the purpose of doing all these measurements on the information? For example, I speak or someone speaks. Why do we need to measure that information? Because transmission of information in an efficient way. We want to transmit as engineers, mainly computer or communication engineers. We are mainly dealing with transmission of information, carrying the information from one place to another place. Of course, when I speak from here to somewhere, a few meters, it can reach without any measurement. But if I want this information to be transmitted or broadcasted to a large audience, or the distances which are much higher, maybe 50 kilometers, 100 kilometers, the voice cannot reach to that distance. Then we need to do some engineering there. So in order to do that engineering, we need to understand some of the characteristics. To understand those characteristics, we need to measure that information. So then we can transmit that information or process that information or store that information with minimum time and minimum space. Because if you see the different areas where information theory is being used, for example, in a DVD where or a hard disk where we store the information, right? Maybe we store the movies or video files or images or some text data, etc. Then we are mainly concerned regarding its space. Hard disk has some space in GBs or TBs. Similarly, DVD has some space. You want to store as much information as possible. So in this context, we want to minimize the amount of information that is stored within the available space. I mean, every information should occupy minimum space so that we can maximize the total amount of information being stored. So how can we do that? For example, I have a video file of 100 MB, but if I have some method so that I can store that in a DVD, maybe with the 80 MB, then that is better. Is there any compression method so that 100 MB can be made as 80 MB and can be stored in a DVD or in a hard disk? Then it is better. But when it is stored as 80 MB, some information is lost instead of 100 MB, right? So what is the effect of that when I watch that particular video file again? All those things I need to consider. So that's why I need to measure it, and then if I measure it properly, then I can process it so that I can store it with the limited space, or process it with limited space or limited bandwidth and so on. Similarly, fax machines to satellites. So, for example, if you consider a satellite communication system where we want to transmit some information, maybe some studios, video broadcast has to be sent from the ground station to the satellite, so that satellite broadcasts that information to different regions across the globe. So, in that case, the information communication from the Earth station to the satellite should go through the free space. There's a lot of distance involved between the Earth, the ground station, and the satellite on the space. So, in this context, how do we need to represent the information? Because when we transmit from here to the satellite, maybe most of the information, if it is lost, then it's a waste. So, how can we achieve efficiency? And similarly, in case of a linguistic, the three classifications what we have seen in the previous slide are mainly based on the linguistic, because this is based on the language structure. For example, if you see English, certain words will always be, certain letters will be always together in a word. You can think about that. So there is always a probability that these two letters will always appear together in a particular word. For example, when I say theory, E and O, similarly, there might be some other words where E and O appear together. So if you consider all the words with maybe 6 letters, then ho- how many words will have E and O together? We can find out a probability there. Similarly, different kinds of mm, words we can think about. And then in economics, stock market, we need to understand how the stock market functions, or what is the probability of this information coming in the next day. For example, one stock is high today, tomorrow, whether still it will be high or it goes down, whether it depends on any other information that has appeared yesterday, and so on. Similarly, in biology, we use the information theory. So now the question is why we need to study information theory. Because, as I mentioned earlier, as computer communication engineers, we are dealing with the efficiency. We need to find out the efficient ways of transmission of data, storage, and processing of the data. For example, this is a different example. We have a fair coin. That means a coin which has a head and tail, and there is an equal probability that when you toss the coin, either head or tail will appear. There is equal probability. So here is a coin is being tossed, then there's a 50% chance that head will appear. Otherwise, tail will appear. There's again a 50% chance. We don't know which one will come until we see the result. There is an equal probability. That's called as a fair coin. So now, when you toss the coin, something will appear. Maybe head will appear or tail will appear. Then, can we measure that? Can we represent this event in the form of a um, measure, information? For example, you toss the coin maybe 100,000 times, and you will have so many results, right? Maybe some of them are heads, some of them are tails. In this so many 1 lakh number of times the experiment is done. And if you want to communicate this sequence to another person, how will you do it? Is there any better way of doing it, or every time you need to say that it's head, it's tail, tail, head, head, and or maybe 50,000 times it was heads, and remaining 50,000 times it was tail, or maybe 60,000 times it was head, and 40,000 times it is tail, and so on. Do we need to say this way, or is there any property we can devise to express these results to someone else? We will see that. So now I am moving to the story of information journey. So until now, I talked about what is information, what are the different sources, and we also thought about a question whether, based on certain events or examples, that whether this information can be measured. We'll see the answers in the next slides, but before that, I want to give the engineering touch or the communication touch to this information concept, information theory concept. So this slide, this figure here, right now we have some information source, and the information source is generated by some so any source, maybe a human being talking or a TV that generates some audio video signals, anything, or maybe tossing a coin, that's also an information. So now we want to transmit this information from the source to some destination here. So this information, for example, voice that generated from the human beings, uh, comes to the communication channel here. For example, when I speak, my voice from my mouth travels through the air, that is the communication channel, and then finally it reaches the destination here to maybe this listeners who are at a distance of 2 meters or 5 meters away. Now, what is the information source here? Or this is nothing but the message, some English words that I speak or someone speaks. And this has to be coded. Why do we need to code? When the distances are very limited, we don't need to code the information. For example, as I said initially here, the distance involved is just 2 or 5 meters. Maybe in a classroom, I speak, then I can directly reach the listeners. There is no need to do any engineering there. I can directly speak. Otherwise, when the distances are too large, or explicitly we need to send the information through specific electric channel, then we need to do something. So here we'll see that what we need to do. So here the message may be some words generated from the information source, and now we do the coding of these messages. For example, this may be voice signal that has to be converted into digital. So because we will be transmitting this information to a large distance through some communication channel, so we need to convert this into digital format. So from the English sentences or voice, it has become 0 and 1 sequences. So we convert this analog signal into digital, so it becomes zeros and ones. That is called as coding here. It's a very general term, coding. And then it comes to the communication channel. Here the channel may be a wired channel or a wireless channel. And from there, okay, in the channel we can have some noise, unwanted signal, or some distortion being added. So that will degrade the signal. And then at the receiver side, there is something called as decoder, because destination is can understand only the English symbols or the voice signals. It cannot understand this 0 and 1, because this destination is also a person. The source of information is also a person. Maybe in that case he cannot understand 0 and 1. He wants to listen to the sound that was generated at the source. So at the destination, we before the information goes to the destination, we use a decoding unit here. So decoder will convert the zeros and ones that have come from the channel here back to English or the audio signals. So for example, it converts the digital into analog and gives to the destination. So here, one term what we use here is called as coding. So basically represent in this context, it is representing the analog signal into digital so that it can be transmitted through the channel. And then at the decoding, we are doing the reverse process of converting the digital into analog so that it can be understandable or interpretable by the destination. So this is one of the targets of information we said initially information is a knowledge that can be interpreted. So here he can interpret what the source expressed his opinion. So here we use the term coding and decoding in a very general way, but we will see these blocks more in detail uh, under the umbrella of our course syllabus. Okay, now I need to mention about an important person here. That is called as, he's called as Shannon, Claude Shannon. He was the uh, PhD from MIT, and he's called as the father of information technology because until he discovered some theories on information representing the information, there were no such theories existed. So he saw different events. For example, maybe someone speaking or tossing the coin or throwing the die, etc. Different events that or the informations he observed, and he thought, can these informations be represented digitally? Is it possible? And then he gave some theories that are relevant even now, and it will be used even in the future. So he envisioned the problem, the biggest problem of communication, that how to reproduce the information at the other side. That is, you transmit the information from the source to some faraway point, to some destination. Then that information should be exactly or approximately reproducible. So to do that, that information should be measurable. So he gave some mathematical framework to measure that information. So he is called as the father of information technology. So he holds a bachelor degree from Michigan and graduate degrees MS and PhD from MIT. So he wanted to find a way for reliability. He wanted to send the information from one point to another point through some channel reliably. Reliable in the sense that can be transmitted with the minimum errors or minimum deviations and at the maximum transmission rate. For example, you have heard about different data rates. For example, you use a 4G cell phone, then you have the download rate. Maybe you experience 20 Mbps or 40 Mbps and so on. So that is the rate, data rate. So he wanted to have that maximal user experience for the data transmission. The best example is here, maximizing the speed of your internet at home. So that's an example of uh, achieving a better or maximum data rate. So he saw these points. There was some information source and there was some destination. This destination wanted the information from this source. So when this information has to reach from the source to the destination, it has to travel a long distance and come through the channel to here. So to do that, the information should be represented in digital, and also that should be transmitted through the channel. When it gets transmitted through the channel, there is a chance of a noise and some deviations acting on that information. So in all these contexts, how efficiently, reliably this information can be sent from the source to the destination? Is there any mathematical way so that we can optimize the performance of our transmission communication? That guidelines, that theory was put forward by Shannon. Okay, now we see in more detail regarding the scenario of this course, that is the information theory. So here we have different blocks that represents different modules of your course syllabus. So first we have data or some information. So this information how can we represent this information? Whether this the data or the information that is represented has some properties? Can this be measured? All that we see in the first module. And then in the second module, we will be seeing this, that is source encoding. Because when the data is generated, for example, I'm speaking, that's some information that is converted into digital, zero and ones, and then it comes to the next unit that is called as source encoding. That is, before this information is being transmitted through a channel, this should be encoded. So that is called as source encoding. So at the source encoding, what is the main deal? So here we will try to minimize the data that is generated from the source with the minimum number of bits. Still, it should be decodable, understandable. For example, I speak 10 sentences. All these 10 sentences are broken down into binary in the form of bits, zeros and ones. So maybe it is maybe 2000 bits. But now at the source coding, we are examining, or we are trying to find out, can we represent all the meaning of these 10 sentences or 2000 bits with just maybe 1800 bits? Still, the receiver can understand that. For example, when we speak something, the other people can summarize our talk. That means they don't speak exactly the words what the speaker actually said. It is possible that you can just produce a summary of that. For example, you read a book, one page, and then you write the summary of that. Then you don't write exactly those uh, that one entire page. Instead, you'll write only few sentences. So that should give you the summary, right? So at the source coding, we do that, and then the data is ready, and then this data has to be transmitted through the channel. For example, maybe a wired channel, maybe a ethernet cable or a fiber optic cable, or maybe a wireless channel like a mobile communication system. But this channel is very cruel. This will degrade the data if you transmit it directly to the channel. So in order to avoid the degradations or the noise effect that channel is going to introduce, we will be using another process here that is called as channel encoding. So before the data is sent to the channel, at the channel encoding block, we will be uh, running some algorithms that is called as encoding algorithms, or the channel encoding algorithms, so that even if the channel introduces a noise, there is little effect on the message that we want to transmit through the channel. So we are basically making this information much stronger by adding some additional bits. So even if that data is getting infected or affected or spoiled by the or degraded by the channel, still that should be readable, decodable. Okay, we will do that at the channel encoding block and send to the channel. Channel, of course, will introduce some noise or degradations or some issues there on the data, and then channel will transmit the data. And here, this is the receiver side. At the receiver side, the first block is decoding. So at the channel encoding stage, we have added some additional bits to make the data much stronger to overcome the effect of channels degradation. Now we just try to remove that additional bits added at the channel encoding. So basically at the channel decoding, we will do exactly the reverse process of channel encoding. Okay, after that we get some data bits, the message bits. Now here it comes, after that it comes to the source decoding. At the source decoding, we will try to decode. At the source encoding, we have encoded. At the source decoding, we will try to decode the effects that are introduced at the source encoding. And finally, we get the output here is the original data that was produced by the source here, or nearly it is same as the data generated at the source here. So this forms the data source, source encoding, and channel encoding. These three forms the transmitter side, and channel is the middle agent that carries the data, and remaining three blocks here forms the receiver side. So in general, source encoding will operate on the information that is generated by the source, where we will try to compress. It's a general word, compress, a general word. But specifically, we do some mathematical operation there. We will see that in the second module. And then in the channel coding, we will try to add some more bits so that even if the message gets transmitted to the channel and if there are some noise added, still there will be no problem with the message that we want to convey, that we do here. And at the decoding side, we will remove all those additional bits added here. And then at the source decoding side, again, we will try to fill up what was compressed here. We are trying to decompress or fill up those additional bits, or we will try to rebuild the compressed data. And then finally we get the almost the data that was transmitted from the source here at the user side or the destination side. So this is the overall picture of this course. The first module here, the data. Second module here. Third module we study this part, and in the fourth module we study this, and in the fifth module we will study some part from here in detail as well as some part from here. So now we have different electronic gadgets here, or the scenarios here, that shows where this information being used or processed. For example, we have the DVD system here or a hard disk here. Both, what is the function of these? They are used to store the data, right? So when we store the data or information, it wants to occupy little space. So we need to sometimes we need to compress the data. For example, you might have heard about MPEG file, the original video maybe in one format. Then we compress it so that we can store more and more data in this disk, more and more video files in this disk. But still, when you play the disk, you can watch the video with a good quality. For example, if you've seen the YouTube video, that where you can select different qualities of video based on their resolution, 1048 or 720, 320, and so on. All these qualities will have the same information, same video, but they have some properties different, so they appear different. Similarly in case of hard disk. And this is a router which is mainly dealing with the channel, because a router either will transmit the data through the wireless channel to your mobile phone or maybe your notebook, or it will receive the data. So again, when the information is transmitted through the wireless channel from the router to the notebook or notebook to the router here, we are dealing with the channel here, right? So the information is again digital information. And then we have the mobile phone again. When you speak in the mobile phone, your voice is encoded and then it is transmitted. So we have the source encoding, those features. And of course, we have the error correction coding, channel coding processes. And also we have the channel here. And you consider the satellite communication picture scenario here, where we have large distances involved. Similarly, we have a wired cable here and so on. So now here, the information theory and the terminologies. So when I say the word source encoding, we usually it can be referred to zipping the file. We use the zipper, right, for compressing different files into one folder, so that the size becomes much less than having individual files. So source coding can be related as something like zipping. We are reducing the size of the file. and decoding is unzipping. Similarly, channel coding. What is channel coding? Like adding CRC bits. This is called as channel redundancy bits, cyclic redundancy check. All this. So this is mainly used in computer communication. And at the decoding, we need to verify these CRC. We will see how to compute these CRC and verify CRC, etc. And these are again the different scenarios as I mentioned. For example, you want to store the information in a CD or a DVD, then what is your information? Information is nothing but a movie. And that movie will be encoded. This is a source encoding where we are converting uh, the movie into an encoded file, that is MPEG encoding, and then it is given to the channel coding part here, that is RS encoding. So this is a special type of encoding, Reed Solomon encoding. We will see that as a part of channel encoding scheme. And then what is here? A CD or DVD where the data is stored. Now we are not dealing with the transmission here because these devices are used to store the data. So instead of channel here, the CD or DVD itself is a channel here in which data is stored. And then we want to watch this video that is stored in the CD or DVD. How do we watch it? We watch it in a TV, right? So we need to have a DVD reader or uh, a device to read the CD. What are the main functions takes place here? One is decoding. That is, Reed Solomon is an algorithm that will decode. The process done here is encoding. The opposite action here is decoding. And then the file is decompressed at the MPEG compression. Here encoder it is compressed, here it is decompressed, so that you can watch in the TV. So here is the source, which is a movie, and here is the destination. You have a TV here, and this information is stored here instead of transmission. Instead of a channel, we here the data is stored. Similarly, this is the scenario of a hard disk, and this is a scenario of a mobile communication. So here we have the mobile phone that generates some voice, or we speak through the mobile phone. So initially our speech is encoded, that is called a speech coding. Our voice is compressed so that it can occupy minimum number of bits, minimum space in the channel, and then we do the encoding here. This is the cha- channel encoding part. CC is convolution coding, represents convolution coding. This is a special type of channel encoding scheme that we will see in the fifth module. And then our voice is transmitted through a wireless channel. And then at the receiver side, that is at the destination mobile phone, these activities are done, which are basically the opposite of what was done at the sender side. Now, we have here measurement of information. We are not next moving to the context of measurement of information. The first question is how to measure the information in terms of bits. This question was put forth by Shannon, and he gave us some theories to measure this information. For example, there are different events such as throwing a die. Here, what are the different possibilities here? When you throw the die, you may get a 1 or 2 and 3, 4 or 5 or 6, any one, right? At one tossing. Similarly, if you have a deck of cards, what is the probability of getting a J? So you should know how many cards totally we have, how many J's we have in a card, and so on. Similarly, we have a picture here. Some area is shown here. Can we measure the information that is represented by this picture? Similarly, we have a deck of cards here. Can we measure the information here from these cards? What is the information we get? Similarly, in case of these dice, can we measure this information? So in order to do that, they should be in a digital format, or we should represent it digitally. So we are moving towards the answer. Can the previous question was, can we measure it? Now the answer is yes. Let us measure it. Shannon said we can measure it using the probability theory, and that is the only way to do this. For example, you consider this tossing a dice. So here, what are the different outcomes once you throw it? It can be one, or maybe two, or four, or five, or six, any one of these. So occurring of every event has a probability of 1 by 6. That is, you have a die here, you just throw it, you get a 2, or you can get a 3, or any number, 1 to 6, right? So for every number, there is a probability of 1 by 6. Similarly, tossing a coin, what are the different possibilities? A fair coin, either head or tail. So all of them, that is head as well as tail, have the equal probability of 1 by 2. So this idea was put forth by Shannon. He said, using probability theory, we can represent any of the events or any of the messages or informations. uh, We can measure them. We can represent that as a measurable quantity. So, how the information is measured? Information is measured in terms of bits, and information rate is measured as bits per second, and so on. We will see those topics in the next lecture. So today we talked about the definition of information, and then we talked about the main question, whether this information can be measured. And we got the key here, that is, information can be measured using probability theory. In the next lecture, we will see how exactly the information can be measured with the help of probability theory, and that will be the first step towards this course. So that is the end of today's lecture.